This is in the rotational motion chapter, the third video on Angular Kinematics. It may or may not be two parts, not quite sure how long we'll see how far we are at the end of this page. And I told you guys back at the beginning of the year that everything we do in translational or straight line, we're also going to do in rotational. So today's where we kind of start to do that overlap. Now, I wrote out the straight line kinematic equations over here. We've got v sub f equals v sub o plus at, x sub f equals x sub o plus v sub o t, so on and so forth. So in order to keep them separate, what we do is we change the letter symbols from English alphabet to Greek. So instead of x, we use theta. X becomes theta. And if you think about it, that makes sense. If you're going in a circle, a lot of times you'll talk about degrees in a circle, and the symbol for degree is theta. Instead of velocity, we'll use, looks like a cursive W, and this is omega. Instead of acceleration, we'll use alpha, and time stays the same. Time is just time. So again, X becomes theta, V becomes omega, and A becomes alpha. So I just rewrite these equations with these variables. So now I'm going to have final rotational velocity equals initial rotational velocity plus alpha acceleration times time. I'm going to have theta final equals theta initial plus omega initial time plus 1/2 alpha times squared. Going to have theta final squared equals, shoot, that's a mistake. I'll grab my white out. Omega final squared equals omega initial squared plus 2 alpha theta. A little darker. And then finally, I'm going to have the change in theta is equal to 1/2 omega initial plus omega final times time. So they really do, they stay the same. It's 1 for 1. And again, we just change the letters so that we can know that we're in rotational and not translational. Now, one of the things that changes in straight line, you could decide what direction coordinate system you want to use. For angular motion, there is kind of a standard. So if you're going clockwise, so this is going to be clockwise, or you could be moving counterclockwise. I'm just going to put CCW. So if you're moving clockwise, that is negative by convention. Now, that doesn't mean it can't change, but usually clockwise is going to be negative and counterclockwise is going to be positive. So that's something you need to memorize. So let's look at a couple of sample problems. Dario, a prep cook in an Italian restaurant, spins a salad spinner and observes that it rotates 20 times in 5 seconds and then stops spinning. Whoops, that's a typo. The salad spinner rotates 6 more times before it comes to rest. Assume the spinner slows down with constant angular acceleration. What is the magnitude of the angular acceleration of the salad spinner as it slows down? So I'm going to do a variable bank just like I did when I did straight line, except this time I'm going to do, instead of initial velocity, I'm going to do omega initial. I'm going to do omega final. I'm going to have theta. And we can do theta. A lot of times for rotational, it's just the change in theta. So I'm just going to put theta. So I'll put a delta there. I'm going to have alpha, and I'm going to have time. So they want to know what is the magnitude of the acceleration as it slows down. And we see that it's coming to rest. So this is going to be 0. So here's the question. I need 2 more variables to solve this. So we have to kind of pick this apart. A salad spinner rotates 20 times in 5 seconds and then it stops spinning. It rotates 6 more times before it comes to rest. So at the beginning of this, we have this. We have that it's spinning 20 times in 5 seconds. And it takes 6 rotations to come to rest. Well, this is going to be equal to my theta value. So what I'm going to have to do, I have 6 rotations, but everything's going to be in radians. So I'm going to have to convert that to radians. So I put 6 rotations over 1, and I have 1 rotation is 6.28 radians. It's 2 pi, right? We don't approximate, we don't leave things in terms of pi. We always approximate pi at 3.14. So 1 rotation is going to be 6.28. So what does this mean if I'm going 20 times in 5 seconds? Well, remember, velocity is displacement divided by time. So this is actually my initial angular velocity. By the way, too, for all of these, we call these the angular displacement, the angular velocity, the angular acceleration. So if I'm going 20 revolutions, and I'm doing that in 5 seconds, I need to convert that to radians per second. So I'm going to go with 1 revolution is going to be equal to 6.28 radians. These are going to cancel, and when I'm done, it's going to give me radians per second. Now, I forgot to pre-work the algebra on this, so I'm going to pause the video, pop that in, and you can do the same. Okay, so let's go through the algebra here. So when I take 6.28 times 6, that's going to give me 37.68 radians. And 20 times 6.28 divided by 5 is going to give me 25.12 radians per second. Let's assume, let's keep all of these values positive. So let's assume we are rotating as we start counterclockwise. So these are going to be positive. So I'm going to have positive 25.12 radians per second. And I'm going to have positive 37.68 radians. So we want to solve for alpha and times the one we're not using. So just like we did back in the beginning, you need to find the equation that is going to be usable here. When you do that, you find that you're going to want to do omega final squared equals omega initial squared plus 2 alpha theta, which was final velocity squared equals initial velocity squared plus 2 times acceleration times the change in x. So let's plug our values in. This is going to be 0. This is going to be 25.12. This is 2. We're solving for alpha, and this is 37.68. Now notice what happens. When I simplify this, I'm going to have 37.68 times 2 theta equals negative 25.12. It's going to give us, I'm sorry, it's alpha, golly gee. It's going to give us a negative value on our acceleration, but that makes sense, right? If our velocity is positive and we're slowing down, that means the acceleration has to be negative. That same rule that we had in translational applies to rotational, that if the velocities and accelerations are the same sign, we're speeding up. The velocities and acceleration are negative signs, we're slowing down. So when I do the math for alpha, assuming I punched everything in my calculator correctly, I get 0.33 radians per second squared. Okay, next one is just a practice problem. So I'm going to scroll down here, go ahead, pause the video, and see if you can find the answer to this one, and then we'll work it out. All right, how'd you do? Let's start off with your variable bank. So we've got omega initial, omega final, theta, alpha, and time. So in this one, we're going from rest. So our initial velocity is going to be 0 to an angular speed of 0.2 revolutions per second. Now, here's another thing. If you're confused about what goes with what label, remember, look at your units. So the, this is going to be in radians. This is going to be in radians per second. This is going to be in radians per second squared. But we have a problem, right? Because this is in revolutions per second. So I'm going to have to convert this. I'm going to take 0.2 revolutions over 1 times 1 revolution is 6.28 radians. So that's over 1 second. So when I do that, again, grabbing my calculator, I thought I had these all worked out, times 0.2, I get 1.256 radians per second. 0.2 times 6.28. Yep. We have 30 seconds, and they want us to solve for angular acceleration, so we're not using displacement. So I'm going to end up using omega final equals omega initial plus alpha time. This is going to be 1.256 equals 0 plus 30 times alpha. And when I take 1.256 divided by 30, I get that my alpha value is 0.042 radians per second squared. And the sign's positive, we're speeding up. So if I have a positive angular velocity and a positive acceleration, that equates to speeding up. All right, kind of thought this might be getting on a little bit long, so we're going to do the rest of the practice problems in a part 2. We're calling this part 1. Okay, on to part 2.